So next up is Dr. Bethany Ehlmann. She's a professor at Caltech and PI of Lunar Trailblazer, and she's going to talk about Lunar Trailblazer, a pioneering small satellite for lunar water and lunar geology.
Okay, thank you. Can I confirm that you can both hear me as well as see my slides in full screen mode?
Yes, we can.
Okay, great. Well, thank you to the organizers, and I'm, as we all are, acutely sensitive to the fact that this is challenging to organize in a pandemic, but I think you've done a great job so far, and I enjoyed this morning's sessions and look forward to hearing about the science and exploration of the future. So adding to that, I'm very pleased to have the chance to talk in this session about our mission Lunar Trailblazer, which is a small satellite for lunar water and lunar geology. I am the principal investigator. You heard earlier in the morning in the panel session from Rachel Klima, who's the deputy PI, and we're supported by the science and engineering organizations here. You see the line on the bottom. So it's a large team behind the effort I'm presenting. What is Lunar Trailblazer? We are a small science mission selected in June of 2019 under NASA's Simplex call. We're a mission to the moon. That's an ESPA Grande ride-along craft, and we're getting a ride on NASA's heliophysics mission, IMAP. We are coming up on our preliminary design review in October, and our mission is supported by both the Planetary Science Division and then transferring after our PDR to SEO. Our goal of Lunar Trailblazer is to understand the form, abundance, and distribution of water on the moon and the lunar cycle. So it ties in very well to the types of missions that Elliot has just articulated here. Our goals are to determine the form, abundance, and distribution of water and hydroxyl on the sunlit portions of the moon, to understand the controls of the variability by latitude, soil maturity, and lithology, to test for and map time variability in water on the moon, and to directly image and determine the form and abundance of water in the permanently shadowed regions, as well as understand the local gradients in terms of temperature. And so these are our driving science goals, but along the way, I think we pick up a lot of data important for exploration, including the best thermophysical properties and compositional maps of candidate landing site zones for our future landed missions. Now, I think everyone on this call is familiar with the drivers, the driving science, and the excitement of the discovery of water on the moon, from the work with the return samples of the Apollo collection showing a relatively wet mantle, as well as the remote sensing data of a suite of orbiters, and culminating with, in some ways, with the L-cross impact and the direct detection of water in the plume. So a number of scientific questions then have remained regarding water on airless bodies, and the Simplex missions and Lunar Trailblazer is one, directly address questions from the decadal survey and are driven by those science questions to determine how volatile compounds are distributed, transported, and sequestered, and what are their inventories. So how will Lunar Trailblazer advance the state of the science of what we know about water on the moon? So we have the beautiful map that I'm showing here in the center portion of the slide of the OH and H2O distribution on the moon. M-Cube discovered the water on the moon, but that discovery was unexpected, and so the instrument was not optimized to characterize the water. Some of the key questions remaining are certain rock compositions or soils of different maturities more enriched than others in water, and does that vary with time on the sunlit side of the moon? Many of you on the phone may be familiar with some of the issues involved in this, so I'm showing on the upper right two different data sets. So the thin lines, the thin dotted lines, are the initial thermal model for Borealis crater, whereas the thick lines are the results from a new thermal model. And you can see that, well, depending on which model is chosen, either there is a water enrichment or there is not a water enrichment. So that thermal correction is really important. Just to bring that point home with an animation, we have a crew of interns working on our mission, and one of them created this great graphic. So you can see here in green the OH-H2O absorption, and how, as we move into the sunlit portions of the lunar day, how that OH-H2O absorption is affected and influenced by temperature. You're effectively getting both the absorption in reflected light and emitted light, which causes this to be a tricky problem. So you see here the wavelength ranges of the two instruments carried by Lunar Trailblazer. HVM cubed will get at the OHH2O portion, while the Lunar Thermal Mapper will independently provide temperature maps. So that is, in effect, the key. Lunar Trailblazer will answer and resolve these questions about the amount of water and whether it is enriched or not in certain terrains by the enhanced spectral range and resolution that I'm also showing over here on the right-hand side, where you can see how M-cubed senses the shortwave part of the key absorption feature, but HV-M-cubed will capture the whole feature to allow hydroxyl versus ice discrimination. And as mentioned before, we also will have the simultaneous temperature to correct these data and get the true water abundances on the surface. Now, the second thing that Lunar Trailblazer is designed to do is to directly image which permanently shadowed regions on the moon have water within those shadowed regions. So the proof of concept was demonstrated with LROC. This figure from Cisneros shows how you can use terrain scattered light, that is light scattered on the surrounding topography, to image directly what's in the crater. And Lee et al. Showed that if you aggregate and average many M-cubed pixels, you can actually, even in the M-cubed data set, pick out the absorptions of water ice frost. So HVMQ builds upon that and will directly image all of the polar permanently shadowed regions at the lunar poles to determine which ones have water ice at the surface, which ones do not, which ones is that hydrogen signature from neutron spectroscopy, maybe in hydrous crust versus ice. And I think a question that many of us scientifically are wondering of, are there organics as well in these ices on the moon, just as there are on Mercury? And what does that say to the delivery of organics to the Earth-Moon system over time? So again, that spectral range and resolution allows us to unambiguously determine and identify water ice and organics with that radiometric sensitivity to do the direct imaging even in the shadows. The data sets will look like this. There's a image cube. It's an HVM cubed is an imaging spectrometer. So for every pixel, we'll have a spectrum, and I'm just showing a subset of the range on the right to get composition, while simultaneously nested within our data from the Lunar Thermal Mapper instrument, which allows that temperature correction, abundance determination, and better silicate mineralogy. And we'll be getting these types of data, nested data sets for multiple portions of the lunar surface, some with coverage at 3 times a day to search for time variability. So just to say a bit more about those instruments that I mentioned, the high resolution volatiles and minerals mapper, HVM cubed, is the legacy of M cubed, which you see here, but miniaturized and improved performance of this spectrometer funded under NASA Picasso development. It's an Offner spectrometer with E-beam grading that's optimized for signal in the 3 micrometer region. So you can see our spectral range spans from the kind of green wavelengths in the visible out to 3.6 micrometers at a spectral resolution of 10 nanometers and at very high signal to noise and uniformity that will allow us to answer these outstanding questions about the form and abundance of water and dependence with thermal properties.
2 minutes, Bethany.
Thanks. The second instrument is the Lunar Thermal Mapper, and it has 14 channels. 6 of them are shared with Diviner, and it has a higher spatial resolution by a factor of about 10. We'll get 25 meters per pixel, and this allows us to get temperature and composition. In the interest of time, I will skip the part about how we get to the moon, but basically we launch with IMAP, which is a heliophysics mission to L1, arc back to the moon, and then enter into a science orbit that is 100 kilometers, polar orbit that is 100 kilometers plus or minus 30. The nature of our data collection is that we're a push broom system. So we're collecting data in targeted areas. The science team has identified 900 targets across the surface of the moon. We're a simplex mission. Our baseline approach is to target the most important areas for resolving these science questions about water. So this is kind of like HiRISE at Mars, those of you who are familiar with that. So we're getting 2% coverage of the moon under our baseline mission in these focused areas for science and getting all of the PSRs. At PDR, we'll be presenting NASA with something we said we do in our phase AB, which is a trade study that shows that by adding radio slices and antenna, this is $5 million, 5 kilograms, that we can get global coverage of the moon as well as serve as a comm relay for potential future assets. Where are we in our timeline? So we are in where the line is in green. We are here. We're in the middle of our tabletop reviews, heading toward a PDR and confirmation in the fall before we proceed to build and then launch on IMAP in 2024. So in the interest of time, I will close with a few thoughts here. Lunar Trailblazer is driven by decadal class science in terms of these questions resolving water on the sunlit surface of the moon and in the shadowed regions. I think appropriate for this forum, we are also gathering important information for exploration, which permanently shadowed regions have ice right at the surface for future exploration and extraction. What are the best compositional maps of the landing sites? And then, as mentioned, we have this option to add global mapping capabilities or service, future service in our extended mission for lunar surface communication. So I'll leave it with that and say you can ask me questions now or check us out on our website or Twitter or email me later. So thank you.
Thank you, Bethany. That was an excellent talk. And we have a couple of questions. So Phil asks, mission end. Will it end with impact, and will science be possible in last few seconds?
Yes, so the mission will end with impact at some point in the future. We haven't done a complete budget, being only a pre-PDR, but we'll run out of fuel and impact the moon like all of the other orbiting missions. I don't know about science the last few seconds, but certainly the last few hours will be then transmitting the highest resolution compositional data as we go down, and maybe rate some radio science along the way as we go down. Yeah, the close-up view at the end of mission.
All right, we have one more question. I think we'll take that in discussion session because we are kind of running on time. So,
okay,
yeah.
Thank you.